Okay. So let's continue talking about Morse theory. So now I want to give some examples of Morse functions on non-orientable surfaces. So I'm going to start with the Möbius band. I'm going to write them. So you could look at the Möbius band inside of R3, and you could just take a height function. The problem is that it's going to be a function that's going to be varying along the boundary. And that's not a very nice kind of Morse function on manifold with boundary. I'll explain this in a little bit, but usually when a manifold has boundary, we're going to want the function to be constant on the boundary. So it's not possible to find an embedding of the Möbius band into R3 where the boundary is on a constant height. So instead, I'm just going to write the Möbius band like this. So my Möbius band, I'm going to identify this side with this side. And I'm going to draw a Morse function here. Okay. So it's going to have two critical points. This is going to be the min, and this is going to be the max. Okay, so this is the minimum of the function, and this is the maximum of the function. So I'm going to show you that I can construct such a function. I'm going to use level curves. So if this is the minimum, then I'm going to basically look at, sorry, this is not a max. This is going to be just a critical point. It's going to be a saddle. And the maximum is going to be attained on the boundary of the Möbius band. So it's going to go like this, and then like this. Okay. So for a saddle, you know that sort of the level curves, they look like this on a saddle. Right? That's basically when minus x1 squared plus x2 squared is equal to 0. That's two lines. So that's consistent. Okay. So now you can kind of see I can do it like this and kind of get it flat. All right. So this is my description of my Morse function on the Möbius band. Okay, so I guess this is a critical point. And the index here, this one has index equal to 0, and this one has index equal to 1. Okay? And then there's no index 2 critical point here. And the maximum of the function is attained along this. But because you're on the boundary, then these are not critical values. These are not critical points. Because they're only critical points if you have a local maximum or local minimum in the interior of the manifold. That's a local minimum in a whole open set. If it's just a local minimum on a relatively open set like this, then it doesn't. It's not. It doesn't. It doesn't have to be a critical point. Okay. All right. So that's the Möbius band. Any questions about this Morse function? Okay. So now I can do, for example, RP2. So RP2 is the next interesting non-orientable surface. And you can think of RP2 like this. So you can think of a bigone, or maybe a circle. So RP2, you can think of it as like the upper hemisphere, or one of the hemispheres of a sphere, where you identify the equator, half of the equator with the other half. So you can take this guy, and you identify with this. So now I'm going to construct a Morse function here that has 3 critical points, one of each index. So in dimension 2, I can have index 0, index 1, and index 2. So index 0 is a minimum, index 2 is a maximum, and index 1 is a saddle. Okay? So I'm going to do the following thing. So I'm going to put the minimum, again, at the, in the middle of my domain. And then I'm going to start, my level curves like this. And then I'm going to put a saddle right here. So this would be a minimum. This would be a saddle. And over here, I have my max. So I can draw my saddle like this. So you see that I can draw level curves like that. And then now, around the max, my level curves, they look like this. And there we go. So that's a Morse function. So I guess I'll leave this as an exercise. I probably will put this on the problem set. Write down, explicitly Morse functions for these two manifolds. Write an equation that describes, for a Morse function that looks like this and looks like that, and also one for the Klein bottle. So exercise. Write Morse functions on the Möbius band RP2 and the Klein bottle explicitly. Okay? And you can do that like on a square. For the Möbius band, actually, the three of them, you can think of them as quotients of the square. So like this guy, you could actually, if you wanted, you could think of it as like this. Something like this, where you identify this and this, and this and this. And then you can actually just construct a function of R2 into R, which is invariant under the Z2 action. Okay. Any questions? And it's interesting because for the Klein bottle, you're going to need two saddles. So two index 1 critical points. So for RP2, you can have a Morse function with one min, one saddle, and one max. And for the Klein bottle, you're going to need two saddles. You're going to need two index 1 critical points. And that hopefully will be clear either later today or on Monday. Okay. All right, so now let's, basically I want to prove a lemma. It's kind of trivial, almost trivial, but for closed manifolds, it's already kind of proven. I want to basically prove that Morse functions exist. Well, we already stated, by Thomson's universality theorem, we know that they not only exist, but they are an open and dense set. But if the manifold is compact with a boundary, I actually want to say that Morse functions exist with a specific condition on the boundary, which is that they will be constant on the boundary. So here's the lemma. Let X be a compact manifold. Maybe we can call this proposition. It's not really a lemma. Let's call this a proposition. Let be a compact manifold with boundary then there exists a Morse function such that the critical points are in the interior of X, and F restricted to the boundary. Well, F restricted to the boundary is identically equal to the maximum, so it attains the maximum exactly at the boundary. And in the interior, it's strictly less than the max. Okay, so you should think of, basically something like this. So, if you have a surface with boundary, a compact surface with boundary, it's not very hard to think about how to put the surface in R3 so that the boundary is all the highest level of the function and not critical. Okay, but this is actually true for any compact manifold with boundary. We can find such a Morse function. I told you, if you want an embedding, for the Möbius band, for example, it won't work. You can't find an embedding of the Möbius band into R3 that makes this work. You can do that like for higher dimensions, probably, for higher Euclidean spaces, but it's kind of complicated. It's just easier to prove the proposition regardless of embedding. So doesn't matter if X is embedded or not into Rn, you can find a Morse function directly with this property. Okay? And the proof is as follows. So, let's assume the boundary is non-empty, otherwise there's really not much to prove. We already know that Morse functions exist. So what you can do is, you can find a tubular neighborhood of the boundary inside the manifold. So there is a neighborhood of the boundary in X is diffeomorphic to the boundary of X. Well, I'm going to put the factor first. Minus epsilon 0 times the boundary of X. And how do you do that? You can, for example, use, that there exists an outward normal or inward normal pointing vector field. I kind of explained how to do that. If you choose a Riemannian metric, then you can choose a vector field that's, say, outward normal. And now you can integrate that vector field. And that will give you integrate it backwards into the manifold. So that will give you, a little. And if you're assuming the manifold is compact, then it's even easier because you can do that for like a finite, a number, some epsilon that's strictly positive. If the manifold is not compact, then the boundary may not be compact, and then it's a little bit harder. You have to. This radius could be convergent to 0, but still an open set. Anyway, but I'm assuming it's compact, so we don't even have this problem. So if this is your boundary of X, then you can find a little strip inside of X. So let me just say this one more time. How do you find this diffeomorphism? You just let phi t. So to do that, we let V be an outward pointing vector field on the boundary of X, and you let phi t that goes from X to X be the flow of V. I guess, you extend it a little bit. You extend it into X as you want. Yeah. Sorry, let's write this down. I'm so used to writing on a tablet now after all this pandemic that I'd like to just kind of circle that and move it down. But you can't do that on a blackboard. So extend it to all of X, or maybe just a neighborhood, but you might as well do that. And then the flow is well defined for negative t. Okay, I mean, for positive t, it's not because you're going to get out of the manifold. But for negative t, if you're doing the flow backwards, that's like doing the flow for minus v. So v will be an inward pointing vector field. So then you can actually, the flow will give you a function that goes from minus epsilon 0 times the boundary to x. That just takes a t and x and goes into phi t of x. And then you have to be a little careful, but basically the flow is invertible. So this will give you an embedding. So that, that just means that when you look at the image, you can flow it back and get back to the original point. So this gives you the desired diffeomorphism. Okay. So anyway, so we have this little diffeomorphism, and then now we can just use this. To be really precise, what you can do is you can let rho that goes from minus epsilon 0 into r be a bump function. Well, actually, in 0, 1, be a bump function such that rho actually, I want the following thing. So I want rho to be, let me just say it like this. So rho is a smooth function. Let me not call it a bump. Well, it's a bump function. I want it to be like this. So I want it to be, I want rho to be identically equal to minus epsilon, near minus epsilon. And I want rho to be, rho of t to be equal to t near 0. Okay, so I want a function that goes like this. So it is not between 0 and minus 1. I want it to be between minus epsilon and 0. So I want it to be, so here's minus epsilon. Here's minus epsilon. I want it to be kind of like this. Oh, it starts in minus epsilon. And I want it to be like this. Okay. So then now, what you can do is you can define a function f that goes from x to r in the following way. So f of x. So if x is equal to phi, if f is in the image of phi, so if x is this phi of ty, then you just define this to be rho of y. Now, rho of t. And then otherwise, you just define it to be minus epsilon. So no, basically what you're doing is, this bump function here is something you could have figured for yourself. But basically, I'm saying you have the tubular neighborhood of the boundary, and you use the parameter of the tubular neighborhood to project this to R. So that goes from 0 to minus epsilon. And the maximum is attained exactly on the boundary. And you just kind of take the rest of the manifold, and you just take everything to minus epsilon. Kind of constant. But this is obviously not Morse, because it's mostly constant. But we can use the Thom transversality theorem. So by the Thom transversality theorem, or by one of the corollaries, of the Thom transversality theorem, we can find a nearby function which is actually Morse, which is transverse to the S1 that we talked about before, which coincides with F on a neighborhood of the boundary. Because there are no critical points here. So over here, the transversality condition is attained. So we can perturb F away from the boundary of X to satisfy the Morse condition. Okay? So anyway, this is just one thing, but you see how it's nice to think about, sort of you have a maximum and then everything that we're interested in is kind of below that maximum. Okay. So, all right. So that's one proposition. Another one that's kind of cool too, to figure out what's going on. So let me just tell you, where we're heading. So the idea is that we want to describe how complicated manifolds can be. But we want to do that using a Morse function. And part of that will be like, if we have a Morse function, can we change the Morse function a little bit so that we can describe the problem in a better way, in a simpler way? So that's kind of where we're heading. So the next proposition is the following. It's basically saying that if you have two critical points, you can assume that their images are different, so that the critical level really only cares about one critical point at a time. Because in principle, if I have a critical point, I could have several critical points with the same image, so that the pre-image of that, you would hit several critical points at the same time. And that's the first thing, that's one thing I want to rule out, or I want to, not rule out, that can happen, but I want to go away from this situation. So, this is very simple, but I kind of think we need to state it. So let X be a manifold, and F a Morse function. Then there exists perturbation. It doesn't actually matter that it's a perturbation. It's just a different Morse function, such that if you have any two critical points which are different, then their images are going to be different. Okay. So that implies in particular, or that's equivalent to saying that every critical level contains exactly one critical point. Okay, so how's the proof? The proof is kind of just a kind of a simple construction, but I think it's good to do it. So first of all, by the Morse lemma, we know that the critical points are all isolated. So if I have a Morse function, I know that in the neighborhood of the critical point, there is nothing else. There is only that critical point, because we know that in a chart, it has a quadratic form, and the quadratic form, there's a unique critical point in that little chart. So by the Morse lemma, the critical points are isolated, or the critical points of F are isolated. So what I'm going to do now is I'm going to perturb the function F on just little neighborhoods of the critical points to make sure that they all have different values, so that the function attains different values. So well, I'm going to assume that the manifold is compact. Again, doing Morse theory on non-compact manifolds is a little bit more complicated, so I'm not going to really talk about that much in this class. So always compact manifolds. And maybe it has boundary, actually. But whenever it has boundary, I'm going to assume that it has this condition. Okay, so I'm not really going to worry about the boundary very much, because the critical points are all in the interior. Okay, so the critical points are isolated. So for each critical point, so I can actually, there's a finite number of them. So P1 through Pn. So for each critical point, for each Pi, we can choose a bump function psi I. So this goes from x to 0, 1, which is supported in a small neighborhood of each Pi. And more than that, that it's identically 1 in an even smaller neighborhood around each Pi. So, or yeah, in a small neighborhood. And psi I is identically equal to Pi near Pi. Okay? So of course I want these neighborhoods to not intersect. So basically each Pi is here. So P1, P2, they're isolated, so I can choose open sets that don't intersect. So I want to choose a bump function on each open set that takes values in 0, 1, such that the support is contained here, and so that it's identically equal to 1 in an even smaller neighborhood. Okay? All right. So now I can, so for epsilon 1, epsilon n, positive numbers, we can define, so we can let f tilde be simply f plus the sum of epsilon I psi I for I equals 1 to n. So, you can kind of perturb your function a little bit. And that's almost the end. You just have to notice that, of course, if you have two critical points that have the same image, then you can choose different epsilon i's. And, it's easy to see that you can get different values for each of these points. The only thing that's not completely true is that, that's not completely obvious, is that you don't add new critical points. I mean, it's kind of obvious that if your critical point, that the critical point set of f tilde is contains the critical point set of f. Because near Pi, very close to Pi, you're just bumping your function by this epsilon I. So you still remain a critical point. And there's no other critical point in this little neighborhood. But maybe, between here and here, you could maybe have some other critical points that show up, because the bump function, is not constant. But if you make the epsilon I sufficiently small, then that's going to solve that. So, because, away from that, that there are no critical points of the original function f in this whole thing. So that means that, in this region here, the derivative of f is bounded away from 0. So that means, if you choose your epsilon I sufficiently small, you look at kind of the maximum of the derivative of the bump function, and you make sure that this guy is never, the derivative of the sum is never 0 near each Pi. Okay, so, we can choose, so for epsilon 1, epsilon n sufficiently small, there are no new critical points. So we get what we wanted. So we get the critical point set is equal in that each of them have a different image. I guess you can say the following way. And the number of points, the number of critical values is equal to the number of critical points. Okay, that's an equivalent to say. Okay, so that's the simple proposition. Okay, any questions about this? Okay, so now what we're gonna do now is we're gonna start looking at the topology of the manifold and how that's determined in some way by Morse functions on the manifold. Okay, so the first thing I want to do is define what a gradient-like vector field is. So let f. So when I write a function like this, I always mean I always assume that x is compact, possibly with boundary. So if I take a Morse function, a vector field V is said to be gradient-like if the zeros of the vector field, if the set of zeros is equal to the set of critical points and whenever you don't have a zero, then the vector field points in the direction of increase of f. So Vf is bigger than 0, Vx of f for x not a critical point. Okay, so the derivative of f in the direction of v is positive whenever you're not at a critical point. So that's what it means to be gradient-like. Okay, so one thing that's not maybe completely obvious is that gradient-like vector fields exist. They do exist, and it's actually not so hard to find one. And namely, you can just choose the gradient of f. But to do that, you have to pick a Riemannian metric. So the differential always is a one form that's well-defined, doesn't depend on anything. But the gradient vector field depends on the choice of a Riemannian metric. So example, so if we fix a Riemannian metric on X, we can define what's called the gradient Well, I'm going to actually write grad. No, I'm going to write it like this. In Riemannian geometry, people like to keep nabla for connections, but we're not doing Riemannian geometry. So I'll define the gradient to be the unique vector field such that, so when you look at G of, so the Riemannian metric is G. G of the gradient dot, that's the same as df. So the inner product of the gradient with any vector is the same thing as df, as the differential of the function. Okay? So you can see that the Riemannian metric gives you an isomorphism between the tangent and the cotangent spaces. And the gradient is sort of the inverse of this isomorphism applied to the differential. Okay? So that's what the gradient is. So the gradient, obviously, yeah, so, it's kind of clear that the gradient is a gradient like a vector field. But the thing is, there's a lot more flexibility in the set of gradient-like vector fields than gradients, because if you just want to look at gradients, you have to change the metric and you have to kind of really see what's going on. But if you can use any gradient-like vector field, then there's a lot more stuff you can do. You can just kind of look at the Morse function and find nice vector fields there that are appropriate to it. They don't have to be, you don't have to look at the Riemannian metric and kind of see what the gradient is like in that representation, because that gets kind of complicated if you're on a manifold. And you look at charts, and then you kind of have to think about what the metric is in those charts, and it can be quite complicated to say that a certain gradient-like vector field is the gradient of some metric. It's much easier to use this definition and to work with gradient-like vector fields in general. But they exist. But there are many more than just gradients of functions, or the gradients of the function with respect to some metric. Okay. All right, so yeah, so now using this, we now let f be a Morse function again. And as I said before, I'm going to assume that if x has boundary, then the Morse function has that property that we wanted from before. So the max is attained on the boundary, and the critical points are all in the interior. Okay, so now I'm going to define the following thing. So for a regular value, so for a regular value A, I'm going to define a submanifold of X, which is the following thing, is the preimage of minus infinity A. Okay? So we've seen that this is actually a submanifold. So this, we proved that a few classes ago, that this is a submanifold. Of X. It has codimension 0. So it has the same dimension as the dimension of X, of codimension 0, and it has boundary F inverse of A. Okay, so now I'm going to have the first, really interesting fact that comes from Morse theory, which is going to start kind of simple, and it's going to get more interesting. But even this, I think, is already kind of remarkable. So proposition. So let f be a Morse function on X. Suppose that that you have an interval in R that doesn't contain any critical values. So suppose this interval doesn't contain critical values of f. Okay. Then XA is diffeomorphic to XB. Okay, so if you take an interval that doesn't contain any critical values, then this manifold, the submanifold of everything that's below A, is diffeomorphic to the submanifold of everything that's below B. Okay, so before the proof, let me draw some pictures so you see kind of what's going on. So say that I have they say that my manifold is a torus, and I have a Morse function, which is the height. And, say, so here's my R. And say I take A here, and I take B here. So you see my XA is this set here, and my XB is this set here. So it's not hard to see from the picture that they are diffeomorphic. And already, what's kind of incredible about this proposition is that we know that the manifold is compact, so we have finitely many critical points, we have finitely many critical values. Which means that already, without knowing exactly how to do it, you can kind of already imagine how the construction will work. Because, so if A is really small, below sort of the image. So the image of your Morse function is a compact set, because the manifold is compact. So it's a compact subset of R. So if you take something that's really small, then XA is the empty set. And if you take A that's really large, then XA is the whole manifold. And what happens is there are changes to the topology of the manifold as you go through the critical values. So as A goes through a critical value, then we don't have this proposition anymore. There will be a change to the topology of the manifold. But most of the time, there won't be. So you see, like over here, like let me draw the picture again, this guy. If you take an A here, between here and here, you have the same topology. These two guys, everything that's below A is going to be diffeomorphic. And then when you cross the critical value, then you change the topology. So you see that the topology is really only changed at 4 points. And most of the time, this proposition is telling you the topology is not changing. So anyway, this is kind of the way that Morse function helps us to build manifolds. Kind of the crucial point is not this proposition, but the crucial point is what happens when you cross a critical value. But before that, you kind of need to see that most of the time, nothing happens. So basically, you start from the empty set, and when you start to look at your manifold from the bottom to the top, when you have the first critical value, something happens. And then as soon as you're after the critical value, then nothing happens for a long time. And then when you have the next critical value, then something happens, and so on. So there's actually just a finite number of changes to the topology. Most of the time, we have a diffeomorphism as you go along the R, and you look at everything that's underneath. Okay? All right, so that's kind of the philosophy. Let's prove the proposition. The proof is actually very simple, but as many things, it's kind of simple, but you need to write them down because it's not obvious. So let V, so this is the proof, let V be a gradient-like vector field on X. And I want it to be pointing outwards if you're on the boundary. So, such that V points outwards on the boundary. Okay. And now I'm going to take a bump function such that psi is identically 1 on the pre-image of AB. And the support doesn't intersect the set of critical points. Okay, so that's supported away from the critical points. And I know I can do that because this interval doesn't have any critical values. Okay, so I can actually, even extend it a little bit and find an open set with no critical values. So I can, so this thing can be supported away from the set of critical values, of critical points. Okay. So then I can define another vector field the following way. I mean, the idea is kind of the same as what I did before. You just want to use a flow that's going to go from here to here. But you want, you want to look at the flow of your gradient-like vector field. That's going to give you the diffeomorphism, but just when you get close enough to A. Away from here, then you want basically the zero vector field. So you define the following vector field. So that you define W to be a vector field as, so Wx will be equal to psi of x times v of x over df of vx, if x is in the support of psi, and 0 otherwise. I guess maybe, what you really want to do is you just want to use v. But v doesn't kind of have the same speed. We're going to do the flow of v, and v doesn't have quite the same speed as f. So you can kind of, as f. So you might be taking this guy to something like this that won't, be a fixed level. So that's why you kind of want to divide by the value of f by df of v. dfx at vx. But then you can't divide by df when df is 0. So that's why I put the bump function here. Okay? All right, so this is a vector field with compact support. So it's very nice. And I actually want to assume that, just for things to make sense, I want to assume that the image of f, that B is contained in the image of f. So I assume that B belongs to the image of f. Because otherwise, if my manifold, if B is way above, then I can't flow all the way there, basically. Okay, so if B is above, is over the, if A and B are over the maximum, then this is obvious. So there's nothing to prove. So it's only an interesting result if B if A and B are in the image, actually. So I'm going to assume A and B are in the image. So in other words, the pre-image of A and the pre-image of B are non-empty. Okay. Yeah, so in other words, the submanifold actually does have a boundary. Both of them do have real boundaries. Okay. So now, this W has a flow. So W has a flow that I'm going to call phi t. And it's kind of a funny flow because it could potentially leave the manifold. So you have to be a little careful. But I claim that this flow, it exists for t between 0 and b minus a. So my claim is that this flow will exist as long as you don't leave the manifold. So basically, if you start somewhere, I guess the main thing you have to check is you can flow because the support is compact, so you won't have a problem with the flow exploding. The only problem you might have is that the flow hits the boundary. Okay? So let me show you that doesn't happen. So how do you show that doesn't happen? So what I would like to do is I would like to compute f of the flow of a certain point. And I want to show that that's still between A and B, actually. So I'm going to show that if you start with something between A and B, so I guess the first thing that I'm going to show is that if x belongs to xa, then f of phi t of x belongs to xb for every t in this interval. So I can actually flow by time all the way up to b minus a, and I will still land in xb. Okay? So that's a simple calculation, just using the fundamental theorem of calculus. So this guy minus this guy f of x. So this is equal to the integral from 0 to t of this derivative. So the derivative here is going to be df of the derivative of the flow. So df of w. At the point phi t of x, or phi s, ds. Yes? Não tem nada mais. Você poderia ter pego o gradiente. Mas aí você realmente, no caso de ter borda, você tem que tomar um pouco mais de cuidado. Você tem que dizer que o gradiente, o borda é ortogonal à função. Você tem que escolher uma função, uma métrica riemanniana que seja ortogonal ao borda. Então é um pouquinho mais complicado falar de gradiente. Assim, nesse caso não tem problema, você podia usar o gradiente mesmo. Mas, assim, em geral, dá um pouco mais de flexibilidade de poder usar qualquer gradient-like. Tá, beleza. Okay. So I guess the point we have to see is like this guy here is actually bounded. So what is df of w? So df of anything, of wx, wy, so this is going to be, psi of y. So it's either 0 or it's psi of y times 1. So this is less than or equal to 1. So of course, if y is in the support, so let me just write it like this. Df of this guy, of y, this is either psi of y or 0. So this is if y doesn't belong to the support and if y belongs to the support. But in either case, you see that this is less than or equal to 1. So that means that this integral, n bigger than or equal to 0. So that means that this is greater than or equal to 0 and is less than or equal to 1. So that means that, f of phi t of x is going to be bigger than or equal to f of x and less than or equal to f of x plus t. Mm-hmm. sorry, less than or equal to t. Yeah. Thank you. T. Because this is less than or equal to 1, so the integral is less than or equal to t. So that means I can keep integrating this, and the only way to get out of the manifold is if I get out of the range. So the only way to get out is if I actually hit a point where the boundary, kind of stops where I hit the boundaries. But as long as, because I'm assuming that B is in the image of F, and it's a regular value, so it'll be basically I can go all the way to B minus A. Okay, so this implies in particular, so the flow maps XA into XB. And this is well defined for T between B0 and B minus I. I mean, if you're really, really concerned about the manifold with boundary, I mean, if you don't have a boundary, then you don't really have to worry about leaving the manifold. But if you're really worried about leaving the manifold, you can kind of think the following thing, like for starters, you can assume that B is in the interior. So B is not, the pre-image of B doesn't intersect the boundary. So, sort of your boundary is here, and B is somewhere here. So then, basically, you can find a way to close up the manifold so that you don't have to worry about that at all. Like, you don't have to worry about the flow existing. It will always exist for every time. But in particular, it will actually be bounded over here. So it will even exist within the original manifold. Okay, but anyway. Or you can just kind of think about the case with no boundary if that's, if you don't want to think about that. But anyway, the point is that we can define a flow, and the flow goes from XA to XB. So phi P minus A goes from XA, and the image is contained in XB. And then now you can actually look at the opposite flow, the flow with minus B minus A, and that takes XB to XA because of the same calculation. And of course, the composition of the two flows is the identity. So basically this guy is the desired diffeomorphism. Okay. So that's it. Any questions? Is that clear? Okay, so now actually I want to do a 5-minute break because I need to get colored chalk. I won't be able to do the second hour without more colors. And drink some water. Uma pausa de 5 minutos. Okay. Well, I have the colored chalk, so we can talk about what happens when you go through a critical value. So, so far I told you that mostly nothing happens when you vary the parameter of the Morse function. The topology of what's below this parameter doesn't change. But as you can see, even from the simplest examples, that's not true when you cross a critical value. So that's kind of the big question now. That's what I want to explain, is what happens when you go through a critical value. So So the question is the following. So suppose A is a critical value of f, and f is a Morse function, and it has the property that all the critical values correspond to a unique critical point. Okay? Let me just write the whole sentence. It's Morse such that, well, the number of critical values is equal to the number of critical points. The question is, how is xa minus epsilon related to x of a plus epsilon? So how does the topology of xa change when you go through the critical value? Okay? So let's analyze this little by little. So let's suppose that let's suppose that that A is the image of some critical point where P is the critical point of index 0. We're going to start with the simplest case. So what happens if P is a critical point of index 0? That means that near P, we can write the function as basically P is a local minimum of the function. So that means that in a chart near P, we can write f of x, this is equal to a plus x1 squared plus etc. plus xn squared. Okay? So in a chart near P. So what happens is that near P, f of x is always greater than or equal to a. So near P, actually, this manifold here is empty. So that means, I guess let me write in a chart near P. So in some U, which contains P, f has this form. So that means that this manifold, it actually could exist because this is just a local description near P. But this means that this neighborhood does not intersect xa minus epsilon. Okay? And on the other hand, what is xa plus epsilon intersected with U? Well, if I'm inside this neighborhood U, then if this is less than or equal to a plus epsilon, then it's the same as basically the ball of radius epsilon. So this is just equal, or diffeomorphic to a ball of radius epsilon, which is contained in U, completely contained in U. So that means that when whatever you had before this, so this means that your xa plus epsilon is going to be equal or diffeomorphic to xa minus epsilon, this joint union with this ball. Well, actually, I should say one more thing. Sorry, before I say this, I should say one more thing. Outside you can use the same argument as before to prove that xa minus epsilon is diffeomorphic to xa plus epsilon minus u. Okay, so like if I don't look at u, what's happening inside of u, then I can do the same diffeomorphism as before, just using the flow. Okay? Because I don't have critical, because remember P is the only critical point in this level. And everything else is right, nearby I don't have any other critical points and any other critical values if epsilon is sufficiently small. So the conclusion is that xa plus epsilon is going to be diffeomorphic to xa minus epsilon, this joint union with a little ball. Okay? So let me draw a picture of an example so you kind of see this in action. So let's say my surface, I have a surface like this. And I'm not going to draw. No, yeah, I am going to draw. Follow. No. Okay, so let's see this picture here. What's happening here? So I have this critical value here, this critical value here, A1 and A2. And I have this critical value here, but I'm not going to talk about it yet because it's not index 0. But anyway, these two are local minimum, so they're both index 0. So let's see what happens when you cross A1 and A2. So when you're below A1, then you have nothing. You have just the empty set. What happens when you cross A1, if you use this recipe, basically you're supposed to have nothing, the empty set, plus a little ball, which is exactly what happens. After you cross A1, what you have, and now I can start using my colors, is a little ball. See, this is a two-dimensional ball. And as I vary between A1 and A2, because of the proposition, and you can also see that in the picture, I get diffeomorphisms. So these are all disks. I don't change the topology. Until left, I cross A2, and then there's a sudden change. And what's the sudden change? When I go above A2, when I go above A2, I have the same thing as before, the same disk as before, but now I take the disjoint union with another disk. So this is what happens. Every time you cross a critical value that corresponds to an index 0 critical point, you just get a new connected component that's given by a little ball. So the number of connected components goes up every time you cross an index 0 critical point, or every time you cross a critical value corresponding to an index 0 critical point. Okay, so that's it. That's what happens. Well, that's the index 0 case. Okay, so let's see what happens when you cross higher indices. I guess I can, let me do the index n also, because it's very similar to this. So what happens when you cross an index n critical point? So that means, if the index is n, so that's the maximum index, that means that in U, my function will look like x1 through xn is f of p, or a, minus the sum of xi squared, I equals 1 to n. So kind of what that means, it's kind of like what we had there, but upside down. So you kind of flip, you just kind of flip the sign. So what does it mean here, really? So it means that whatever I had before, so basically in U, when you look at x a minus epsilon intersected with U, that's going to give you basically everything that, you can assume that U is just like a ball of, I don't know, radius delta or something, centered around 0. Where delta, and when you look at what's between epsilon and delta, what's less than delta, you're going to get some kind of strip like this. So, I'm assuming that U in this kind of chart is some ball of radius delta. So this x of a minus epsilon, so when this is less than or equal to a minus epsilon, then, this is kind of diffeomorphic to some ball, my original ball of radius delta, minus the ball of radius epsilon. And when I go through the value of a and I go above the value of a, then I guess I just kind of fill in this ball. Okay? So, if you just look at this expression, when you put a plus epsilon, that's the same as just putting a. You can't go above a. And that's just going to fill this up. So then basically a plus epsilon intersected U is just going to be sort of this whole, all of U, if you want. Which, for me, that my U is this ball of radius delta. Okay? And what happens is outside of this U, it's kind of the same thing. I don't change anything. So what's happening is that my x a plus epsilon is diffeomorphic to my x a minus epsilon union some ball. But this union is no longer a disjoint union. It's actually a union along the boundary of this ball. So I'm gluing this ball and closing something up. So I kind of have to know that there exists some sphere here, some Sn minus 1 here, that's waiting for my capping ball. So that's waiting for a ball to, boom, cap that. Okay? So like, for example, if I have say I have the torus, and I'm over here, and I want to see what happens when I go through this point. So when I'm over here, the manifold that I have is this thing here. And when I go through the index 2 critical point, I go from having this guy to gluing in a two-dimensional ball, which is a disk, that just kind of, boom, closes it up. Okay? Like another example is, say you take the heart-shaped Morse function, but I'm going to perturb it so that the critical values are, the critical points have different images, and say you're over here. So this is my heart-shaped Morse function. So when I look at this manifold below here, I actually have something that just looks like this. It's actually a cylinder topologically. So when I go through this critical point, through this critical level corresponding to this guy, what I do is I just, boom, cap this one, this hole right here. And then when I go through the other one, I just cap the other one. And you can really see that this is the same as the index 0 when you just look upside down. And in fact, if you have your Morse function, you just put a minus sign in front of it, all the index 0 critical points become index n critical points. So it's not too surprising that, topologically, it's basically the same thing. I guess the only kind of difference here is that when you're always looking from the bottom up. So from the bottom up, when you go through an index 0 critical point, then you take the disjoint union with a ball. But from the bottom up, when you go through an index n critical point, then you glue a ball, but it's not a disjoint union. You really have to glue the ball to what you had before. Okay? You know, another way to think about this is like when you're in index 0, this ball that you're kind of just putting there as a disjoint union, it's going to be glued to something above. It doesn't like sit as a disjoint union by itself. Okay. And that's just because, you know, the epsilon is small enough, so if you just move the epsilon a little bit, then you're going to have more of the manifold. Okay. All right, so we've now analyzed the index 0 and the index n. And now I want to analyze index k when k is between 0 and n. And that's now is where the fun really is. Okay. Any questions? Okay, so now let me go here. So now let's suppose A is f of p, and the index of p is equal to k. So that means that in some neighborhood u, we can write f like this. F of x is equal to a minus xi squared from I equals 1 to k, plus the sum I equals k plus 1 to n of xi squared. And now I'm going to draw my picture. So I'm going to draw the picture in 2 dimensions, but I think you'll see kind of how this picture generalizes to higher dimensions. So this is my rk, and this is my r n minus k. So now I'm going to write, so basically, you know, you can kind of see here that you have, so here's the level curve, f equals to a minus epsilon. And here is the level hypersurface, to be more precise, f equals a plus epsilon. Okay, so you know, f equals a minus epsilon will be the set of points of the form, you know, minus xi squared plus, so from 1 to k, from k plus 1 to n equals minus epsilon. And then the other one is that equals plus epsilon. So these are hyperboloids of higher dimensions. So these are all kind of hyperboloids of higher dimensions with different properties. But you know, kind of what I want to show you is basically what you can do is, so if you kind of look at a neighborhood of 0 here, so you can kind of look at a neighborhood of 0, and you see why I'm kind of drawing it like this. So outside of a neighborhood of 0, of course, we can do the same gradient-like vector field, you know, with kind of the divided by the norm or divided by the value of the derivative, so that it really, when you're outside of this neighborhood of 0, then I really have a diffeomorphism. So if I call this object here, I can call this object H. And what is H? I mean, H is really like, I can look at, you know, what's the subset of x, y in Rk times Rn minus k, such that the norm of x squared with a minus sign plus the norm of y squared is between epsilon and minus epsilon. This is really the object that I am adding to x a minus epsilon to get to a plus epsilon. or actually I want to maybe intersect this with, I think I wrote this down. Yeah, like maybe say, I want to say norm of x times norm of y is less than or equal to delta. Okay, something like this. Okay, so that's why I drew these curved things here. So basically, what is x a minus epsilon? X a minus epsilon is this green part here. This is my x a minus epsilon. And the x a plus epsilon is everything that's kind of between these two curves here, or inside this hyperboloid. So basically you can see the following thing. So first I'm going to write down what's kind of obvious, and then we're going to kind of describe it. So how do we construct x a plus epsilon? So basically there are three pieces. There is the x a minus epsilon. Then there is this h. And then there is a trivial part, which is this part here. Everything that's between a minus epsilon and a plus epsilon, that's away from the critical point. And that, I can use a gradient-like vector field to say that it's basically a product. So this is basically, you look at what happens when you look at the boundary of x a minus epsilon minus h. And then, or I guess, you can just kind of say, f inverse of a minus h. And you remove everything that touches h. And you multiply by, minus epsilon, epsilon. So some kind of trivial thing. Okay? So this is the crudest description. This is kind of the first description. And this is basically obvious. Like, the one thing that maybe you want to do is you want to make sure that you can choose a vector field that's kind of, that's parallel here. But this is, pretty easy to do. Like, you just kind of use the vector field that, did I write this down? I think I did. Yeah, so you can kind of choose a vector field that's given like this. So kind of x1, xk, and then minus xk plus 1, and then minus xk minus x. No, I think the minus is here, and the plus is here, xn. So this guy. And then when you look at the flow of this, so this is a vector field defined on this whole neighborhood. And using a bump function or something, you can kind of extend it away from this neighborhood to like the gradient or something, if you want. Or you can do something different. You can look at the gradient of f, and then you can choose a metric that's just the Euclidean metric in Rn, and then you can just look at the gradient of this function. And it's going to be exactly this with a 2 or whatever. Okay, but then the point is, if you look at this vector field, which extends outside of this neighborhood, so outside of this neighborhood it's fine. You divide by the norm, and what it does is it's going to preserve the flow of this guy is going to be, like e to the minus t x1, e to the minus t xk, and then e to the t, or I can write it like this. So it's going to be sort of minus x and y. So the flow is going to be e to the minus t x and e to the t y. So in particular, it's going to preserve this norm and this norm. It's going to preserve the product of these norms. So that means, it's actually, it's going to actually be tangent to the boundary of H. And it's going to do exactly what this is doing in this picture. I mean, this picture is kind of the two-dimensional picture for k equals 1 and n equals 2. But this, what I wrote here, the equations actually work in any dimension. I mean, it's kind of trivial in the case k equals 0 or k equals n, which is why I did them separately. But anyway, we have this. So using the flow of V, we really see that what's left, what's not in X, A minus epsilon, or in H, is exactly a product, like this. And these guys touch on the boundary. So this is not a disjoint union, but I think it's kind of clear where they touch. OK? Are there any questions about this? This is kind of like analytic geometry on steroids. Like hyperboloids in k index k inside of Rn. It's not something that's usually seen in an analytic geometry class, but that's what it is. OK. So what I want to describe now is kind of what these sets, like what this H is really. Because one thing you can kind of see is like at least if you forget about the smooth topology, if you just think about sort of the continuous topology, you can do the following thing. So you can kind of contract this direction. So you can kind of contract the minus epsilon direction. So what happens when you do that? When you contract the minus epsilon direction, then this guy here just kind of gets contracted to the boundary of x a minus epsilon. And the handle also, sorry, I haven't said this word. I was trying to keep it to myself for now, but this H, sort of this guy here, gets contracted here too. So if you contract this, at least in the continuous topology, what's happening is that sort of the green set and the red set, they coincide here, and then they coincide here, and then they go like this. And then your H becomes this thing here in the middle. Okay? I mean, the H already has a nice description. This is a really, really nice description. But what I would like to do is actually, I want to compress this and see at least in terms of continuous topology what I'm doing. Of course, this is like, smoothly speaking, this is a little funny. So I'm going to kind of I'm going to explain what you do smoothly later, but like at least continuously, it's kind of clear that you can just collapse this. There's no topology in the cylinder. So anyway, so you do that. So let's see what this H is. Let's see kind of what's happening to the continuous topology by simplifying the problem a little bit, collapsing this cylinder. Okay, so really what you're doing is you're actually only adding this H. Maybe I can call this H bar. So what is H bar? Well, H bar is something that when you collapse this guy, you just have this part and you have this part. So let's look at what this part is here. So first of all, I guess the first thing to notice is like what is H intersected with this guy? So I claim that this is homeomorphic, or diffeomorphic even, to Sk minus 1 times a Bn minus k. So a sphere of dimension k minus 1 times a ball of dimension n minus k. So this, this set here is this part here. So this part here. You see why I needed colors. Otherwise, I'd be drawing white on white. OK, so what is that? So I want to be on the boundary of H, and I want to be here at the same time. So basically, this is the set of points. So this is the set of xy in Rk times Rn minus k, such that Well, minus epsilon is equal to norm of x minus norm of x. Let me write it bigger, because people need to see online too. Minus epsilon is equal to minus norm of x squared plus norm of y squared. And norm of x, norm of y is less than or equal to delta. Okay. So I actually have prepared this pretty nicely. Usually, at first when I started explaining this, I was just kind of hand waving. But then I actually wrote down a formula. So here's the formula. So I claim that the formula to show this diffeomorphism here. So the claim is that this guy is diffeomorphic to sk minus 1 times bn minus k. So let me first wave my hands, because I think it's actually probably better than drawing the calculation. So why is this guy, why should you believe that this is really a sphere times a ball? Well, look at this orange thing here. So what is this? What are these 2 points here? So this is really just the sphere on Rk. So this is contained in Rk, and this is the sphere in Rk. So this is the set of points such that such that the y is equal to 0, and the x has a fixed norm. The norm of x squared is equal to epsilon. So this blue guy really is a sphere. So this guy here is an sk minus 1. Because of the dimensions here, these are 2 points, it's an s0. But in general, in higher dimensions, I can try to draw a picture in higher dimensions. This is going to be a sphere of dimension k minus 1. And then the rest, when you let the y vary a little bit, but you still fix this condition, then you're thickening this inside of a neighborhood, inside a manifold of dimension n minus k, inside a manifold of dimension n minus 1. So that means that when you thicken this, thickening it is really just multiplying by a disk of, by the tubular neighborhood theorem, for example. This is just by multiplying it by a disk or a ball. I guess I'm calling it a ball. It's the same, a disk and a ball, of dimension n minus k, which is what you need to get to the dimension n minus 1, which is the dimension of the boundary. So this is kind of the hand-wavy way to see this diffeomorphism. Okay? But we can actually write down the calculation explicitly. So let's see if I can do this. Oh, here it is. Wow. So proof. So I can actually define our max, which is sort of the maximum y that's attained here. So if I let this, what is the maximum value of y that's attained by this guy? So it turns out that if you do a little calculation, basically for norm of x, norm of y equals delta, if you want to satisfy this equation and sort of the maximum here, then you have a nice formula, which is just by the quadratic equation. I'm going to write it down. Minus epsilon plus the square root of epsilon squared plus 4 delta squared over 2 to the 1/2. So that's the maximum value of y that's attained. So now you define your diffeomorphism. So it goes from, so usually when you don't write the radius, you just mean radius 1. Okay, so the sphere of radius 1 times this into rk times rn minus k, and that takes xy to epsilon plus y squared to the 1/2 times x, and then y. There we go. So, what this is doing is just you're really looking at sort of the units, the actual unit ball, because this guy is not, norm 1. This is norm epsilon. So you're looking at the unit ball, and you're looking at the map that goes like this. So like you're looking at the unit ball times some ball of radius r max, and then you're looking at some map that does that. And it's not very hard to check, I guess. Wow, my notes are very nice here. Anyway, I don't know if I'm going to recopy this, but actually maybe this is something that instead of me rewriting my notes, you can do it yourself. Check that this, first of all, this is, the image of this is contained in the set, and is actually equal to this set. So I guess you can check exercise. Phi of psi is an embedding, and the image of psi is exactly equal to this guy, to H intersected F inverse of A minus epsilon. Okay? So that's what it is. And by a very similar argument, you can find out what this other guy is. So similarly, when you intersect H with F inverse of A plus epsilon, this is diffeomorphic to BK times S n minus K minus 1. Okay? So it's kind of the same thing. So you have your sphere in Rn minus K, and you thicken it. And that's what it is. Okay? So now, the last thing to notice, and we're getting really close to a nice description, is like what happens with H when I collapse using sort of this map here. So using the map, when I collapse using basically this direction. So the relation that I want to collapse by is the following. So I want x and y to be equivalent to e to the t, e to the minus t x and e to the ty when the norm of x, norm of y is equal to delta. Okay, so this is what I was calling the h bar. And my claim now, and maybe this is something that I can leave you, have several days to do this, and it's very kind of similar to this kind of game that I played here, is what is this h bar topologically? So this h bar is this guy here topologically, and I didn't collapse this part or this part. So this part, the description topologically here is still the same. So can you think of a manifold whose boundary has two parts? One of them is sk minus 1 times bn minus k, and the other one is bk times bsn minus k minus 1. Well, the claim is that H bar, at least topologically, at least as a topological manifold, this is homeomorphic to bk times bn minus k. Okay. I mean, of course, kind of topologically, this is also a bn. Like, this is homeomorphic to just an n-dimensional ball. But the point here really is that I want to think of this n-dimensional ball with the boundary that's separated in two parts. So, like once you collapse, what's the situation that you have here? So you had an original manifold, and you were gluing this H bar in the following way. So first, you're dividing the boundary of H bar in two parts. So you can think of the boundary of H bar here in two parts. So I basically have, first I have the boundary of this guy times this guy. So I have the sk times a bn minus k. And then I have the bk times the sn minus k minus 1. And what I'm doing is I'm saying, take my H bar, and I want to glue it to my manifold in the following. So first, I want to just take part of the boundary of H bar and glue it to this boundary like this. And then I add my H bar. And then the rest of the boundary of H bar is actually going to be the boundary of the glued thing. So this is kind of the procedure. And this H bar is called a handle. So H bar. So this claim, I really want to leave this as an exercise. I think it's instructive for you to construct this, this map, this homeomorphism. It's a very straightforward homeomorphism, really, kind of like this. So I think you should try to figure out how to do that. Probably the easiest way will be to build a map like this. Okay. So kind of the conclusion. So this H bar is called a K handle. And the conclusion is that A plus epsilon is diffeomorphic to X A minus epsilon union a handle. And maybe you are a little not sure about what I mean by diffeomorphic because there's some funny thing about the smoothness, and I'll explain that next time. And this process here is called attaching a handle. So this process here is called handle attachment. Okay, so we're running out of time. So next time, I'm going to explain this a little bit better and give lots of examples and explain what's happening with the smooth topology here and why it looks like this is not smooth, but it'll be OK. OK? But for now, I really would like you to, you have a problem set to work on this week, but I also would like you to try to prove this claim. Try to understand why, after you collapse, you have an obvious identification with the product of two disks. Sort of one disk, you can kind of see here in this picture, it's not so hard to believe in dimension 2. They have an interval times an interval, but I think I would like you to do something kind of similar to find the natural identification there. Okay. Oh, and I have two pieces of information. One is that the exam is going to be in 2 weeks. So 2 weeks from today, there will be the exam. And I actually changed my mind. And for the external students, I will give you the option of doing the exam online. But just to the external students. The IMPA students need to come here for the exam. And for the external students also, I'm going to schedule like an oral test based on the exam, based on the written test right away. So Tuesday, the exam is going to be from 9 to 1. And then in the afternoon, I'm going to meet with some of the external students. So if you're an external student and you'd like to have a grade like ABC, first you have to be doing the problem sets on Google Classroom. So I have to see that. And then send me an email and say that you're interested, and we can set it up. I think there are not so many people that have done all the problem sets. But for the IMPA students, it's just a normal class. So, para os alunos do IMPA, a prova vai ser daqui a 2 semanas, às 9 horas, de 9 a 1. E vocês vão entregar a prova e pronto. Okay, and one more thing. Next week, I'm planning to use one of the classes just to meet with you online. So probably it'll be around this time. So a week from now, from 1 to 3, we probably won't have a lecture, and we'll just have a meeting on Google Meet for everybody who is external. Okay, because we've already kind of covered enough material. I think with 2 classes, we can cover more, and then maybe 1 more class the following week. Okay, that's it. Okay, see you next week. Oi.